Hey, we got a question right here.
Do you still want us to wear a lab coat this week?
I would read the instructions for check-in. Instructions for check-in will tell you everything you need to know. Okay, let's get started. First off, if there's any issues with the videoing ever, let me know. Try to put it on the board what I think is good, but if you have suggestions, can't see something with the video. Okay, any questions about the syllabus?
No.
Okay. Question?
Is the final, I know it says like the date, but I think it's not.
It's from Wednesday,
It's like
May
Wednesday.
6th, but May 6th is a Friday.
And then on the website it says Tuesday.
Well, it's supposed to be Thursday. Did I not write it correctly on the syllabus?
You're a Wednesday.
When you were Wednesday, May 6th.
Mine says Thursday.
On what? That must be May 6th. Yeah, it's supposed to be Thursday, May 5th.
On the back of the first page at the top,
Yeah,
it
on
says the this.
important dates for this class is correct. Yeah. I forgot to change that from last year when Mike on that. Yeah, good catch. The exam is on a Thursday, unfortunately, which is new. I mean, this is the Monday, Wednesday class, but the exam is on a Thursday. Other questions about the syllabus? Questions about guidelines for lab reports, guidelines for lab notebooks? Okay, let's pick up where we left off. Again, the green sheet is our outline. What we'll be doing, we're doing substitution reactions of alcohol right now. We did some basic reactions with Atex to make alkyl halides. Lucas test, we're on tosylates. Tosylate is a way to make an OH a good leaving group. You actually convert it to a new compound that can be isolated and purified. And then the tosylate, this oxygen will now leave. We do not, no acid required. Tosylate is the most common. I do show you mesylates, triflates. We also see something like diethyl sulfate. These are esters of sulfuric acid. But the R group, nucleophile, can attack the carbon. And the O, sulfonyl, can leave, okay? It is symmetrical, but that can leave just like you attack here, and that can leave. Of course, when it leaves, what do you get? 3 carbons, the nucleophile is now on the carbon, plus your leaving group. So it's going to leave, it takes on a 3rd lone pair, and then it's got the sulfonyl, and then the R group. That's generic for aromatic. This is a toluene. You do need to know the full structure. Why will this leave? Because it's very stable. What makes it stable? Largely resonance. These electrons move here, these electrons out, and we can get resonance structure. Okay? So it's resonance stabilized oxygen, and it will leave. It's actually just as good as leaving group as like iodine and bromine for Sn2. You do not need to protonate this oxygen first. If this was like O-methyl or OH, it's not going to leave. The only way to get those to leave is to protonate it. So you have to do it under acidic conditions. These are good to go. Most of these things tend to be very toxic because they'll react with the nucleophiles in your body. We do need to show mechanism for how to make the tosylate from alcohol tosyl chloride. Let's do that. Let's do that now. In that mechanism, we're going to see a very important step that we're going to use throughout the course. Okay, tosyl chloride. It's basically your sulfonyl. There's your toluene group. Over here we have a chlorine. Oxygen is going to replace the chlorine, so it is a substitution. We also have pyridine. Pyridine is a weak base. So sp2 nitrogen. The lone pair is a hybrid. It is slightly basic. Okay, this sulfur here is electron poor. It's got all these groups kind of sort of pulling on it. Boom. These electrons will attack the sulfur. When you attack the sulfur, what do you want to do next? Or maybe at the same time? Ultimately, we got to kick off what?
Chlorine.
Yes. But here's the big thing that I mentioned. Okay? We're not going to kick the chlorine off directly. Now, your book may do it because your book lies to you until they later tell you the truth. Okay. Whenever you attack an atom and you're going to kick something off, you're going to break off the weakest bond. Which is a weaker bond? Sigma bond to chlorine or pi bond to oxygen? Pi bond to oxygen. When we do this, electrons come in, it pushes these up. Or you can push those down. Either way, it's symmetrical here. We do not immediately kick off the chlorine. If an atom is pi bonded, if we immediately kicked off the chlorine when that came in, what type of mechanism would that look like? It would look like an Sn2. You don't do Sn2 on an atom that is pi bonded. If it's pi bonded, the pi bond's going to break. So what does this arrow movement here give? You should be able to draw that. I reckon I'll start by showing the sulfur. Single bond to O. How many lone pairs on the O now? There's two there. Now three, that's a minus charge. What else is bonded to the sulfur? The incoming oxygen. We didn't lose the H. We didn't lose the propyl group. How many lone pairs left on this oxygen? One. That's a charge, because it's not a common bonding for oxygen. What's the charge? Plus. Okay? What's the charge of the sulfur there?
Neutral.
It's still neutral. Sulfur is group what? Under oxygen? On 6. One of each bond. 1, 2, 3, 4, 5, 6. Neutral. Still neutral. What do you want to call this step? Some just general terminology to help us keep track of what we've done. Nucleophilic what? Addition. Simple enough. We added a nucleophile. Nucleophilic addition. Okay, what do you want to do next? Now, we will have to keep track of protons, and we'll say that throughout the semester. All right? When you handle a proton, you can do it different places in your mechanism. I'm going to wait. The next step is these electrons, are they going to come back down? And now we're going to kick off the chlorine. What does this give? Well, what does that arrow movement give? I got the sulfur. What is this doing?
Making a double bond.
Remaking the double bond. So it's double bonded that oxygen again. We still have the double bond down here. Chlorine's gone. Now to keep from getting bad, ugly bond angles, I'm going to put the phenyl group, or the R group over here now. And what's over here? The O. We haven't done anything to the H. And we haven't done anything to the... There we go. Alright? I just drew this over here so it's more sort of correct bonding. What do you want to call that step? What do we ultimately do from this intermediate? Elimination, we can call. I mean, you could call it high bond formation and elimination. Typically just elimination. I'm going to label that A and this B. And going from here to here, what have we ultimately done? We replaced the chlorine with this alcohol group. So ultimately, we did substitution. Now, we haven't taken care of the proton yet. This is our product shown here, just we haven't lost the proton yet. That's a substitution we just did. Okay, in organic 1 you learn 2 substitution mechanisms. You learn Sn1 and Sn2. Which one is this? Is this an Sn2? Sn1? Sn1 involves cation. What's the first step of an Sn1? Leaving group leaving. You might have to activate it so it then can leave, but leaving group leaving. Did the chlorine leave first?
No.
It ain't Sn1. What's Sn2? Nucleophile in, leaving group off at the same time. Did we do that?
No.
No. We have a new substitution mechanism. What do you want to call this? I wrote it on the board as A and B. It's an addition elimination mechanism. Okay? Addition elimination is a 2-step substitution process. This is what you do when you have a pi bond. Okay? Because whenever this comes in, you don't break the chlorine first, you break the pi bond. All right? We will do lots of addition elimination reactions throughout the semester. Overall substitution, it's neither Sn1, Sn2, because you're going to review that stuff, right? This is not Sn1 or Sn2. But it is substitution. Why do you think we include the base? Now we're going to use it at the very end. These electrons bond to the H. Where do these 2 electrons go? Move on to the oxygen. What do we get? We get final product plus what? Okay, I haven't shown. What do we get here? Pyridine is now binding to the H. Got to have balance of charge. That side is neutral. This side looks like it's got a positive. We got to have a minus somewhere. What's the minus that we can also show? Cl minus. We make our product plus pyridine hydrochloride. This is the hydrochloride salt of pyridine. If we didn't include pyridine, what could take the H? I didn't even draw it here, right? I didn't even draw, no, we need to draw it right here, right? When I get kicked off, if there was no pyridine, chlorine could take the H and we would make that plus what? ACl. A lot of times you don't want ACl to form in your reactions because it's a strong acid, it can lead to side reactions. You include a little weak base in here to consume the acid. And you don't get ACl, but instead you get the hydrochloride salt of pyridine. It's sort of more of a neutralization. Okay? Be careful. Pyridine is not strong enough to deprotonate and make this minus. Pyridine, though, look at this. This almost looks like H3O plus. It's a positive oxygen with a proton, just like H3O plus is. See, this is very acidic. Pyridine will take this H, but it won't take that one. Okay. Now the book, see the book introduces nucleophilic addition elimination over in wherever, chapter 18 or 19. That's when they really talk about it. At this point, they may lie to you and they may do like an Sn2. It's unfortunate. They just don't want to get into all this early. But we're going to do it correctly because it's going to set the stage for lots of chemistry, especially the second half of the course. All right, let's see how we did for homework. Questions on erasing? Tosyl chloride pyridine, what's that going to convert the You're going to start with alcohol, what you're going to convert it to? Oscillate, okay? We're going to have boom, boom, boom. That's the deuterium O TOS. Okay? You do need to be able to know this full structure here. Okay? Do we expect any change in the stereochemistry when we make it tosylate? No. No chemistry takes place here when the oxygen attacks the tosyl. Okay? You're not doing any chemistry here. So no change. Now when we come in with, what is NaN3? What's the name of that? Sodium azide. Sodium azide. What's the charge of N3? Minus. Okay, you should be able to draw a Lewis structure. You did that in organic 1. We used azide in organic 1. Now, to be kind of precise, let's draw it out. It's all double bonded. There you go. This is minus, and that's plus. For a net minus, either end is the same. These electrons do what? Attack. Attack here, kick off the tosylate. What mechanism are we doing?
Sn2.
Sn2. And we get what? Boom, boom, boom. I'm just going to call this N3. We just draw this out. It's basically, it's neutral. Because once this bonds, that becomes neutral, and then you got a plus and a minus. It's this here with this bonded to the carbon, and so there's only one lone pair there now. I need to look at that. What do we expect now with the deuterium? Yes. Sn2 with inversion. There's your product. Azide's a good nucleophile. We don't need acid to make this a good leaving group. It's already a good leaving group. That's the purpose of turning it into a tosylate. How we do on that? How about the next one? What does N-butyllithium do to, what do we got here? A alkyne? What's N-butyllithium do? Yeah, we got a terminal alkyne, got an H. N-butyllithium is just a plain carbanion. It's one of the most basic reagents around. Very strong base. These electrons take the H. These electrons stay behind. What do we get? I'm just going to call that phenyl. Get a lone pair here. That's what this arrow means. This electron's moving on to that carbon, lone pair. The lithium can sit there with that. And what else did we make? Butane. Carbanion, very basic. We learned about the stability of an sp carbanion in organic 1. That's just an acid-base reaction. Now we throw in dimethyl sulfate. Remember that? I mean, that's sulfate with minuses on the end, each end. Put H's there, it's sulfuric acid. What is dimethyl sulfate? It's that there. Fully covalent. Remember, we just showed this up there, right? These electrons do what? Attack carbon, kick off the oxygen. Okay? Either end, it is symmetrical. It usually only supplies one alkyl group. And so, what are we going to get? Boom, 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 boom. And now this is bonded to a CH3. Of course, the leaving group was that there. And if you want to keep track of your spectator ions, the lithium sits with that. That can be washed out in the water if you're doing extraction. Neutral product will go into your organic layer. The ionics will go into your water layer. You can separate out your ionics. So pretty straightforward examples of using tosylates or like diethyl sulfate, dimethyl sulfate. Remember your Sn2 inversion, acid-base chemistry with alkynes, etc. Largely reviewed from what we were doing in Organic 1, right? Okay. Now we're going to go back to making alkyl halides. We're going to see some new reagents though. New reagents are going to be SOCl2, which is known as thionyl chloride. Should be in your textbook written out like that. Or PX3, with X being a halogen, like PBr3. Okay. You may be familiar with PBr. This is PBr3. Okay, this is better than just HX for primary alcohols. It's also good for secondary alcohols. HX is great for tertiary. Hopefully you're kind of already thinking about why. We're also going to have some stereochemical comparisons. Now, for example, you take a primary alcohol reacting with TCl3 or thionyl chloride, you can convert it to the alkyl chloride. React with PBr3, you get the alkyl bromide. SOBr2 is just not that common. With the SOCl2, the only one that's common is really the chlorine isotope. Not isotope, but analog or derivative. We can look at mechanism here. Let's do it with the thionyl chloride because I think it's going to be more useful for us in the long run. First off, blue structure, you should be able to give it a good go. It's actually very similar to tosyl chloride, right? I mean, over here it looks like tosyl chloride. Just instead of like an aromatic or an alkyl, it's got another chlorine. Thionyl chloride is a liquid. I'm sorry. It's only SO, yeah. It's like this. But it's still similar. It doesn't have the, it's not a sulfonyl. It's, and actually in terms of blue structure, there is a lone pair there. Because the sulfur does have 6 valence electrons. Not quite as similar as your tosyl, but it's okay. Up here, but the first step is these electrons do what? We're going to attack this sulfur. The sulfur is pretty electrophilic because it's got all these electronegative groups pulling on it. Question?
What's the geometry of that? Is it planar?
Is this? How many electron
Or is
regions
it-
around it? 1, 2, 3, 4. 4 regions. You expect tetrahedral. Problem is sulfur uses d orbitals. If you drew it like this, which is a resonance structure, this may look more tetrahedral. I'd have to think about the use of the d orbitals. This to me is more classically tetrahedral. Of course, when you do resonance, there's no change in any geometry. So whatever this is, it should be the same thing. But it takes a little bit of thinking because of the possible participation of d orbitals with the sulfur. Okay, nucleophilic addition. What do you want to do at this point? Electrons up, just like we did before, right? What do we get? We're going to get, this becomes minus chlorine. I'll draw the other chlorine here, and I'll bring in the new alcohol here. H here, that's plus. What do we do? Nucleophilic addition. And we remembered whenever you add to an atom, there's a pi bond, you break the pi bond. Right? Don't kick off the leaving group. What do you want to do next? Typically, we could take care of that proton, although here there's no base. These electrons now move back down. Now kick off the leaving group, either one. And what do you want to call this step? Elimination. So we did addition, elimination. Just like we said before, that we were going to do a good bit. What does this give? Sulfur with double bond. Chlorine. The other chlorine's gone. OH. Boom, boom, boom. Plus what? Plus Cl minus. Now we're set up for just a beautiful next step. What do we ultimately want to do? What do we ultimately want bonded to this carbon right here? 3 carbons and a chlorine. We want a chlorine here. Does it look like a nice step for this to now come in here and do this? What's the leaving group? Oxygen? It's a protonated oxygen. I mean, it's like best of both worlds. This gives us final product by an Sn2. What was the leaving group? So what else do we also form? OH. Everybody with me? Everybody believing me? Seeing me? There you go. There's your product. Now this over here is not the end result of this. When you do this reaction, if you fully show byproducts over here are product plus SO2 plus HCl. That's the byproducts that come out. And both of these tend to be gases if there's nothing else around. A lot of times you do this reaction and you start kind of heating it, and then gas will start coming out the smokestack, i.e. condenser. And you put some litmus paper up there, it'll turn red because of the HCl being produced. Okay? So what's the mechanism in going from here to here? First off, what type of reaction is it going from there to there? In Gen Chem, you learn like 5 types of reactions. What type is that? Decomposition. One molecule turning into 2. Which is typically driven by what? Entropy. Mechanism for that. Well, I'm about to make another statement here that we're going to make about 350 times throughout the course of the semester. Here's number 1. Anytime you can make a pi bond, you kick off a leaving group. That's usually a fast and easy thing to do. All right? These electrons move in and kick off the chlorine. We're going to move in, make a pi bond, kick off a leaving group. That's usually fast. What does that arrow movement give? It's going to give a sulfur, double bond to O. Now it's double bond to O over here. There's still an H. 1 lone pair left, and that's a positive charge. By the way, there's a lone pair on every sulfur here. Sometimes I didn't drop it. There's a lone pair there. What else is here? Cl minus. Okay? Now, how do we get home? These electrons take the H, these electrons here, and there you go. There's your SO2 and HCl. SO2 is a sulfur double bonded to each oxygen. That's driven by entropy. That's the end result. Here we go. Let's say it for the second time. Anytime you make pi bond, kick off the leaving group, easy to do. We're going to be doing that a lot. Okay? Why is this mechanism that I showed here best for primary alcohol? It's also good for secondary. Because what the actual getting the chlorine on is done by what mechanism? Sn2. Now that doesn't mean you couldn't possibly do an Sn1. It just goes back to here. If you want to substitute off this oxygen from that carbon, are you going to do Sn2 or Sn1?
What was the question?
If you're going to do a substitution here and kick off the oxygen, you get a chlorine on that carbon, are you going to do Sn2 or Sn1? Sn2, because it's a primary carbon. I mean, duh. That's just basic, okay? If that was a tertiary carbon, what mechanism would you want to do? Sn1. Just because you got this fancy leaving group, can you not do an Sn1 here? Sure you can. You just make the leaving group leave first and then do your chemistry. So the basic Sn1, Sn2, it's always the same. Jordan?
Yeah, okay, so this is like this whole mechanism. Technically, there's an addition, elimination, substitution, and then an Sn2 substitution.
Well, there's lots of pre-activation
Okay.
steps. But what I say is getting the leaving group, getting the new thing on the carbon is ultimately, this step is an Sn2.
Okay.
Yes, there were several steps to activate it. The reagent, you get to this activated point. But what we have here is a great leaving group. Not only is it oxygen, it's positive charge. It's also going to be, this here helps, there's going to be resonance into the oxygen. It's an alternative to just using HCl, and it works a lot better with primary alcohols. Something about this leaving group ability is just better than if under my hand was just another H and water was leaving. Okay. Okay, PBr3 is just like PCl3. I'm not going to do it. Try it on your own. We'll see if there's any questions. There's no double bond to oxygen, so it's not going to be an additional elimination. It's going to be a direct substitution. Okay, we might do it next time if there's questions about it. Ultimately, it's the same outcome. So let's do it down here. So we have a reaction. We also have stereochemistry here. Okay, we're going to see lots of reagents in organic 2. Okay, and there is some memorization with your reagents, like note cards, as I mentioned in the series. Okay, what's PBr3 do to an alcohol? Converts it to what? Alkyl bromide. Okay? Halide, bromide in this case. Alright? So you just got to know. So that's a little memorization. But then what needs to kick in is your mechanistic knowledge. And that you cannot just memorize. Because that you need to have fundamental understanding. Try to memorize every single mechanism, you're just not going to work. Okay? So we're converting this to a BR. Well, what about stereochemistry? Because here we have certain stereochemistry. So when we do reaction 1, we're going to get, boom, boom, we're going to get a BR here. It's going to be dashed or bold? Dashed. It's actually going to be dashed. Why? Because to get the bromine on, you got to kick the oxygen off. Now, typically, these reagents are going to do Sn2 for primary and secondary. This is secondary. Okay, that's there. We'll see what type of questions come up. And you think about it a little more in the next time asked. All right. I am doing Sn2, so I am showing inversion. Now when we come in with KCN, which is my favorite reagents, what's happening now? Cyanide's a good nucleophile. These electrons here kick off the bromine. And what do we get? We get a bolded CN. And we're doing two Sn2 reactions essentially. The first one converts the OH to a better leaving group, but not to a tosylate. But you can convert this to a bromide. And the bromide's a good leaving group. Do you need acid to make Br a good leaving group?
No.
No. You see, this is essentially another way to make OH a better leaving group. But it's not really any trick to it. It's just a standard conversion. But just remember, we can do this. And now the bromine's a good leaving group if we come in with a good nucleophile. But you get two Sn2s, and we get back to that in stereochemistry. Let's do the same reaction down here. What's the product down here? All right, what does tosyl chloride pyridine do to an alcohol? We're going to make tosylate. What's the stereochemistry of the tosylate going to be? Why is it going to be inverted?
It's the same. It is the same.
Why would it be inverted? Think about it. It would not be. When we make tosylate, does any chemistry take place at the carbon here? No. The oxygen bonds to the sulfur. Oh, no chemistry takes place here when you make tosylate, because the oxygen is still bonded there. See, up here, the oxygen no longer bonded. We got the bromine on by a backside attack. No change. Now when we come in with KCN, what are we going to get? These electrons attack here, kick that off, and what do we get? We get inversion, which yes is actually going to end up being an enantiomer of the electrons. Because this sequence we only had how many Sn2 inversions? Only one. That sequence up there gave us two inversions. The main difference here is when you do this, you get inversion getting your leaving group on. Here, you don't get inversion because you didn't really change the oxygen. You just put something on the oxygen. Larry?
So the CN will take precedence over the chlorine, the byproduct of the tosyl chloride. You got a Cl minus.
Well, two things. First off, when you make a tosylate, you're going to purify this. That Cl minus that's here, the pyridine, there is Cl minus here. Cl minus, it is an anion. It's a pretty lousy nucleophile though. It's one of those cases where I said that anions are good nucleophile. But chlorine is so electronegative, it's just electron greedy, and it doesn't like to get those electrons out there. You know how we say oxygen's a good parent? Well, chlorine is such a good parent, it won't even let the kids out of the bedroom. It just holds them. And remember, we said, what did we say about F minus? F minus is just a lousy nucleophile. I mean, F minus is like keeps the kids in the closet, you know. So usually that chlorine doesn't attack. Like you make the tosylate at room temperature. To get the chlorine attack, you probably need pretty high heat. The other thing is, cyanide is a better nucleophile than chloride. Because here you got a C minus. C minus is just not a good parent. I mean, carbon's not a good parent. If it's got electrons, it's going to let them get out there. Okay? Cyanide's a pretty good nucleophile. Okay, so there we go. You got stereochemical comparisons that we did there. Versus tosylate versus going to like doing an alkyl halide conversion. All right, green sheet. That finishes up substitution there. Substitution. Now we're going to do elimination. We did some of this in Organic 1. We're going to eliminate water. Loss of water from an alcohol is going to give what type of product? Alkene. Okay? Elimination reaction. Eliminate water. Most common way to eliminate water from an alkene is to use acid. But you have to be careful about what acid you use. You can't use HBr because that won't eliminate. That'll give you substitution, give you an alkyl bromide. You need to use acids where the anion will not attack. And those we mentioned in Organic 1, typically like sulfuric, phosphoric acid. You can use HF because F minus typically won't attack.
Would HCl be okay here or
No,
no?
HCl is borderline. Typically, your Cl, Br, and I minus will attack. Now, of course, you might could do it, but for us, I'm telling you, the lower three halogens will attack. F minus won't. I'm trying to just give you a clear demarcation. Nice word, right? I don't know what it means, but I think it works. Okay. I could give you a lot of examples where F minus does react. All right. But I think let's just say that it won't react in this way. That's what I told you in Organic 1. All right. Because it's very reluctant. All right. So let's do this. Take this alcohol, react with H2SO4, we get an alkene. Let's do this mechanistically, and let's see why it can only be alkene. And what mechanism? Does it already say E1? Or did you get that right by having some good knowledge? Okay, let's just work through it. What's the first thing you want to do here? We got the alcohol, we got acid. What do you want to do first? Yeah, we can show this as H plus, HSO4 minus. It's okay to just draw it like that. These electrons attack H plus, and we're going to get boom, boom, boom. Protonated OH. Now, of course, that's still bold, right? Just like before. That's going to be bold until we attack here and kick it off and do some inversion at this carbon. We haven't done that yet. So everybody should be able to protonate an alcohol. I've said this before, but keep this in mind. Whenever you're doing something under acidic conditions, usually the first thing you're going to do is protonate something. Okay? All right, what do you want to do next? Well, what is the anion here? It's HSO4 minus. Now, is this going to attack and kick off the water?
No.
Especially know if you remember, hey, these anions do not attack. The conjugate bases of the acids I show you are always just spectator ions in this class. So since that can't attack, what can this do? What can happen? The only thing I know that it can do is just leave. And if it leaves, we call that ionization. What does that do? Carbocation plus water. I'm going to show the water as just leaving. Okay. All right. Now, what do you want to do next to get the final product?
Proton, and then on the other side, and then the electrons.
We need to remove the H, put in the pi bond, give us a double bond. Okay? And we did a little of this in Organic 1. It's just going to be, and overall, what is the mechanism, T? E1. E1. We had to activate the leaving group first, but ionization followed by the fast beta elimination. Fast step. And if it's a fast step, any base can do it. We're just going to do it with this conjugate here. But I'm going to do an extra step first, one that gets at the stereochemistry. First off, if you do an E1, what alkene do you get? Thermodynamic, which is the most stable. So why did I say we get that and not these? Because that's the most stable. Why is it the most stable? Because it's trans compared to that one. Why not this one?
That was
These two are called what?
Disubstitution.
Yeah, but they're called a name. Setsef. This one's called, okay, E1's always going to give Setsef, but in addition to that, it's always going to give trans, if possible. Because E1 always gives the most stable. But look at this. These are sort of cis. Well, let me just take you back, and you have free rotation here. And this thing can rotate, and we can get boom, 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 right? Which side's going to be favored, left or right?
Right.
Correct. This is just like when we were doing Newman projections, right? And rotating things. This is like sin, and this is like anti. See, that's going to rotate. So this is going to be favored. And at this point, what's the last step? We got H's here. Something removes it. Now, I like to use the conjugate base. You can also use water. But if we use this, I don't have it drawn out. It's okay to just be a little bit non-precise and just show electrons coming. Take the H. Well, let's take that one. So that I can now move these in. And when you move these in, what do you get? You get that. What did we reform? So H2SO4 is actually what in this reaction? Yes. It's just an acid catalyzed dehydration of an alcohol by an E1 mechanism. Product down below. Can you show product down there? The acid catalyzed dehydration of an alcohol by an E1, super common. Usually when you're using those acids, that's one of them. So ding, 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 this is going to be what? What type of product? This is the dehydration reaction by the mechanism we just did. We're going to get double bond up here, right? As opposed to there? That'd be Hoffman. We're not going to get Hoffman. More substitutes, right? Here's one for you to do on your own. And let's look ahead a little bit. We're going to see a new method to eliminate or dehydrate an alcohol. And it's going to be using POCO3 pyridine. And this is often, I say, POCO, because it kind of reads like POCO, POCO3. Pyridine. The OH is going to be activated as a dichlorophosphate ester. Big word, but it's very similar to when we did that SOCl2. And then it's going to undergo an E2 mechanism. The pyridine is strong enough to do an E2. And you're going to have a stereochemical requirement for E2. You remember that from organic 1? The H in the leaving group must be what when it eliminates? Coplanar with anti being highly preferred. Okay? What I want you to do is to do this mechanism. as I give you some steps up there, and then predict some of these products. Okay? Need to be working on this stuff right here. We'll hit it quickly next time. See what type of questions. Hold on. Lab this week, we're checking in. Instructions are in the lab manual. After check-in and safety information, we'll go downstairs and we'll have NMR lecture. I sent the NMR handout by email. You should print that out. I'll get more information when we're checking into lab at 2:30 each day. Any questions? I think that's it, guys. See you later.
You smell good. Me? Yeah, thank you.